Okay. From the first formula for thermal expansion, delta L is equal to L naught alpha delta T, okay, where delta L is the change in length or linear expansion. L naught is the original length. Fine. Alpha is coefficient of linear expansion. Delta T is the change in temperature. So based on this formula, I want you all to derive SI unit and dimensional formula of alpha. Do this quickly. Derive the SI unit and dimensional formula of coefficient of linear expansion alpha. I'll give you all 2 minutes. Right. See, delta L, which is basically change in length, will be a length itself. Fine. So left hand side, or you can write alpha is equal to delta L by L naught delta T. Delta L and L naught will have the same unit, same dimensions, so they'll get cancelled. So basically, alpha will have inverse dimensions of temperature, or the inverse unit of temperature change. Okay. Now, temperature change. For temperature, the SI unit is Kelvin. So delta T also, the SI unit will be Kelvin itself, per Kelvin, or Kelvin inverse, you can say. Dimensional formula will be K power minus 1. Okay. Now, delta T, okay, keep this point in mind, all of you. This is very important in heat and thermodynamics. Delta T indicates change in temperature, okay? Now, changes in temperature on the Kelvin scale and Celsius scale are equal. Exact temperature may not be equal. For example, 0 Kelvin means minus 273 degrees C. Okay. 1 Kelvin means minus 272 degrees C. Right. So exact temperatures are different on the two scales. But change in temperature, change equal to change from minus 273 to minus 272 on the Celsius scale. So here the change in temperature is 1 unit or 1 Kelvin. So keep this point in mind. Changes in temperature are equal on the Celsius and Kelvin scale. So per Kelvin change is same as per Celsius degree change. Okay. So they can express alpha, like in problems, they can express alpha in terms of per Kelvin or per Celsius degree also. And actually, in Indian books and question papers, they don't bother much about this. But there is a difference between degree C and C degree. Okay. C degree, you read it as Celsius degrees or centigrade degrees. This is used to indicate changes in temperature. Okay. So if you notice, I have written C degree per Celsius degree here. Okay. So that indicates per change in temperature on the Celsius scale. And remember, changes in temperature are same on the Kelvin scale or Celsius scale. So they can write Kelvin inverse or Celsius degree inverse. It's the same. Okay. And in our question papers and textbooks, they write degree C inverse. You have to understand that that is also valid. Okay. Fine. Now, beta, gamma will also have the same units, but understand what they mean. Okay. First, alpha. The formula is delta L divided by L naught delta T. Now, delta L changes relative change in length. Okay. Multiplied with 1 by delta T or divided by delta T, you can say. Okay. So, relative change in length per unit change in temperature. That is what is alpha. Okay. Similarly, beta in area divided by initial area multiplied with delta T. Now, change in area divided by initial by the temperature change. So, how do you define beta? Relative change in area per unit change in temperature. Okay. Similarly, gamma. Gamma is change in volume by initial volume. That is relative change in volume per unit change in temperature. So, this is how you define the different coefficients of thermal expansion. Okay. Now, practically speaking, the values of alpha, beta, and gamma. Okay, just a moment. Let me look up the values. Right. So here it says coefficient of linear expansion of steel is between 11 and 13 into 10 power minus 6. Okay. So alpha of steel is between 11 and 13. Let us approximate it to 10. Okay. Approximately 10 into 10 power minus 6 per Celsius degree or per Kelvin also you can write. As I said, they are the same. So it's approximately 10 power 5 minus 5. Okay. So alpha values of metals will be in that range. It's a very, very small number. Fine. And I told you there is a relation between alpha, beta, gamma. We will derive that. But let's first solve one problem based on alpha. Okay. Basic direct question. A steel rod, let's say it measures 2 meters at a temperature of 20 degrees C per Celsius degree. calculate the temperature to which it must be heated. Uh, let's say we want it to extend by 2 millimeters. Okay, so 2.002 meters. Okay, solve this, all of you. We want the length to be 2.002 meters. Okay, at 20 degrees it is 2 meters, so it should expand by 2 millimeters. Fine. Now for it to expand by 2 millimeters, you can say that the change in length is 0.002 meters, and we know change in length is original length. Okay, 2 multiplied with alpha multiplied with delta t. Okay, I'm using the formula for thermal linear expansion directly. That's all. So we get delta t is equal to 0.002, that you can write as, okay, 0.02 divided by 2 into 10 power minus 5. So that is 2 into 10 power minus 3 divided by 2 into 10 power minus 5, which is basically 100. Okay, you can write it as 100 Kelvin, or you can write it as 100 Celsius degrees also, because changes in temperature are equal on both the scales. Okay. So the change in temperature has to be this much. Now, how much is the initial temperature? 20 degrees C. Now, from 20, if you increase it by 100, the final temperature becomes 120 degrees. Correct. Okay. So, assuming the alpha value of steel is 10 power minus 5, this is the answer. Right. Now, we just saw that alpha is delta L divided by L naught delta T. Right. So, you can say that delta L by L naught is alpha delta T. What is delta L by L naught? Change in length by original length, which is basically relative change. So they may ask questions based on this also directly. And you know how to find out percentage change also. Percentage change in length or percentage change in any quantity is relative change in that quantity multiplied with 100. So that becomes alpha delta T into 100. So relative changes, percentage changes based questions also can be asked, and they are quite easy to solve. Okay. Next. Uh, See, based on temperature, the length of an object changes, right? Now, one of you quick, we use a normal measuring scale to measure small lengths. Now, the measuring scale, depending on the temperature at which it is placed or used, the readings will change. Okay, just a moment. Let me download an image of a measuring scale. Okay, consider a scale like this, and let's say there is a rectangle whose length you want to measure. So how do you do it? You align the scale such that the zero of the scale coincides with one edge of the rectangle and the other edge. Okay, as you can see here, it is approximately 7 centimeters. The length of this rectangle, as indicated by this scale, is 7 centimeters approximately. Let's say this is at some 20 degrees C. Now, if you raise the temperature of the scale, okay, only the scale, not the rectangle. If you raise the temperature of the scale, it will undergo thermal expansion. And as I said, thermal expansion happens in all directions. So basically, you'll have to enlarge it. Okay. So it becomes something like this. Let's say this is at some, okay, we have to consider melting point. Okay, we don't know what it is made up of. Let's say this is at some 200 degrees C. Okay. Let's say it is made up of a material which can withstand 200 degrees C. Now, if you check the length of the same rectangle using this scale, okay, it's the same scale, but it's used at a different temperature. That's all. It will definitely show you a reading less than 7 centimeters. Okay, it's showing approximately 6.3, 6.4. So, based on the temperature at which the scale is used, you may get correct readings or wrong readings. Okay, let's say this scale was calibrated at 20 degrees C. What do we mean by that? Scale is calibrated at 20 degrees C means at 20 degrees C, the markings are correct. Okay, so the correct length of this rectangle, let's call it L naught. The correct length of, fine, not L naught. Let's call it L correct, is 7 centimeters. 7.0 also you can write. Okay. But at 200 degrees C, the scale's calibration will be wrong. Okay, it means the markings on the scale or the readings indicated by it will be wrong. So this there is an error in measurement here. Okay, so the wrong length indicated by the scale is fine. I feel it is 6.3 centimeters. So there is an error in measurement. Okay, you should be able to calculate such errors also. Basically, how much is the error here? Actual reading is 7, indicated reading is 6.3. So the error, okay, is 0.7 centimeters. Okay, it is wrong by that much. Or you can say percentage error also. Delta L by L into 100. Okay, delta L is 0.7. See, this is not expansion. I'm not talking about thermal expansion here. I'm talking about the variation in the reading shown by the instrument. Okay, so the variation in length shown by the instrument is 0.7. Correct length is 7 into 100. That becomes 1%, 1 or 10% error. Okay, so let's see how to solve this kind of problem. These are very important. These are actually high level problems, JE level. Okay, let me ask you one question first. Consider a normal scale. Let's say the correct length of an object is 10.0 centimeters. Fine. So if you use a properly calibrated scale, it will show you a reading of 10 centimeters. Okay. Now, due to thermal expansion, each centimeter of the scale expands by, let's say, 0.01 centimeters. Okay. So the readings, the markings have become bigger. I want you to tell what is the length. Okay. Estimate roughly. Okay. What is the length indicated by the scale now? Uh, one of you quickly tell me, will it indicate a length greater than 10 centimeters or less than 10 centimeters? If the scale expands, will it indicate a length greater than 10, greater than the original length or less than the original length? Okay, less than 10 centimeters. Correct, correct. So I want you to find out exactly what length it will indicate now. Try. I'll give you all 2-3 minutes. See, there is no set formula for solving such questions. This is kind of a new question. You'll have to uh, apply your own logic now. We want the length indicated by the scale when the readings have or when the markings have expanded. Okay. Understand what is meant by length indicated by an instrument. You look at this example itself. In the properly calibrated scale, each step is 1 centimeter. Okay. Each, what can you say? Each reading that is marked there is 1 centimeter. So basically the length, if see, each unit is 1 centimeter here. So when you are measuring length, you are indirectly measuring how many of those units fit in that length. Okay. And 7 such units are fitting in that length, as you can see. So we say the length is 7 centimeters. Now what happened due to thermal expansion, the unit size has increased. Okay. Let's say the unit now is X. How many X's are there in this length is what you need to find out. The object's length did not change. The scale got expanded, that's all. Okay. So how many X's become equal to 7 centimeters is the question. Okay. It's like that. In this question, you were given 10 centimeters, not 7 centimeters. But this is the approach. Finding out the length indicated by the new scale means finding out how many new units fit in that length. Okay, remember that idea. So basically this, as I said, you have to derive this logic on your own. Okay. Now, original length of that object given in the problem is 10 centimeters. That means in the original length of the object, 10 centimeter units can fit. Okay. How many new units fit is what we need to find out. That's all. Now, due to thermal expansion, each centimeter of the scale expands by 0.01 centimeters. So, what is the new unit on the scale? New unit, let's call it X, will be 1.01 centimeter. Each new unit on the scale will be 1.01 times the original unit. The units have expanded. Fine. That's all. Now, how many of these new units fit within 10 centimeters is what we need to find out. Let's say n number of these new units will fit. So you can say n times of x is 10 centimeters. So the number of new units which fit within 10 centimeters is 10 divided by x is 1.01. Okay. And 10 by 1.01 approximately, I think it will be around 9.9 only. But let's get the exact value. Okay. 9.9. 009901. Okay. Up to 7 decimals it has given. Let it be. So the new length indicated by the scale will be close to 9.9. Obviously, you can see the markings on a normal scale. On normal scale, centimeter numbering will be done. In between 2 centimeter numbers, millimeter markings also will be there. So 9.9 sorry, 9.9 centimeters can be indicated by it. It can't indicate beyond that. It can't indicate other decimals. So the correct answer would be, what is the length indicated by the scale now? The correct answer would be 9.9 centimeters. Okay, that's the nearest marking on the scale which will coincide with the edge of the object. Okay, is this clear to all of you? Any doubts in this? Right. Let us now involve concepts of thermal expansion in this. A scale is calibrated, let's say at 20 degrees C. Okay. Calibrated at 20 degrees C means what? If you use the scale at that temperature, it will show you correct measurements. Any other temperature, it will show you either bigger measurement or smaller measurement. If the scale expands, you will get smaller readings. If the scale contracts, you will get bigger readings. Okay. Let's say alpha of the material of the scale is given 10 power minus 4 per Kelvin. Okay. Again, I repeat, per Kelvin or per Celsius degree is the same. Okay. Both, I mean, the unit size is same. Alpha value is given. I want you to find out percentage error in measurements error in measurement of an actual length. Okay, why percentage error? Find out the actual error. Okay, find out actual error in measurement of an actual length of 20 centimeters. Means the object's original length is 20 centimeters. Okay, at what temperature is this scale used? When the scale is used at 100 degrees C. Okay, obviously, when you use it at higher temperature, the markings will expand. So the reading you get will be less than the actual measurement. Okay, so what is that new measurement that you get and how much is the error in measurement? Calculate that. Do this quickly. I'll give you all 2 minutes. Another answer I got is 0.992. Okay. See, there is a reason I made you solve the previous question. In the previous question, what we discussed is, if you know what is happening to each centimeter, then you can tell what will be the reading shown by the scale. My intention was for you to use that idea in this question now. Okay. So the scale is calibrated at 20 degrees and it is used at 100 degrees. Okay. Maybe if I had given 120, solving would have been much easier. I think I made it a little difficult for you to do this. Let it be. Uh, so at 20 degrees, the markings will be correct. Okay. At 100 degrees, obviously they would expand. So if you can find out how much each centimeter expands, then you will get the new unit. And based when you know the new unit, you can tell how many new units fit in this length of 20 centimeters. That's the idea. Okay. So let's consider, or let's first find out how much each centimeter expands. Expansion is original length into alpha into delta t. Okay. 20 to 100 is a change of 80 units. So each centimeter expands by, how much is this? 80 into 10 power minus 4. Okay. 0.000, no, 8 in 10 is 0.008. That is the expansion of each centimeter. That means the new unit on that scale, let's call it as x, would be 1.008 centimeter. Okay. How many such new units will fit in 20 centimeters is what you need to find out now. That will give us the new reading. Therefore, the new reading would be 20 divided by 1.008. That is approximately, okay, I said you can use calculator if you want. 19.84. We can write other decimals also, 12698. But we'll have to do a little bit of rounding off here. The scale will only have millimeter readings. It won't have readings smaller than that. Okay. So as indicated by the scale, you will have to round it off to here. And if you round this off, I think it will be 19.8. Okay. So the new reading shown by the scale will be taken as 19.8 centimeters. What is the original length? 20 centimeters. 20 is being shown as 19.8. Okay. After rounding off. Therefore, the error is measured value minus the true value. That becomes minus 0.2 centimeters. Vanilla, your answer is fine. If you round it off, I think you will arrive at this answer. Okay. You can even calculate percentage error in measurement. Percentage error is absolute error 0.2 divided by the original length into 100. That will be 1%. Okay, is this clear to all of you? Any questions? Fine. So this is basically how you deal with linear expansion. Now, next thing we have to do is derive a relation between alpha, beta, and gamma. Coefficient of linear expansion, coefficient of areal expansion, and coefficient of volume expansion. Okay. Now, what is alpha? Basically, by definition, it is relative change in length per unit change in temperature. Beta, by definition, is relative change in area per unit change in temperature. Similarly, gamma also. Relative change in volume per unit change in temperature. Okay. Now, how do we relate these? Now, to find out beta, you need to know what is the relative change in area. Area dimensionally, if you see, area is basically length into, area is a product of two lengths. Okay, length into breadth, or if you take circle, pi r square, radius multiplied with radius. If you take ellipse, pi AB, semi-major axis A multiplied with semi-minor axis B, so on. In dimensionally, area is L square. Fine. So if you want to find out, uh, okay, you can express area like this. Consider a rectangle if you want. Let's say original length is L naught and original breadth is B naught. Okay. If it undergoes thermal expansion, length will change, breadth will also change. And that is how the area changes, right? So let's say it expands. Then the new length will be original length into 1 plus alpha delta t. New breadth will be original breadth into 1 plus alpha delta t. Now see, this alpha, the alpha we use for length is basically alpha in this direction. So you can call it alpha in the x direction. And the alpha you use for breadth should be alpha in this direction, which is alpha in the y direction. Now, here we have to discuss about materials in detail. Some materials, uh, they display the same properties in all directions. They show the same properties in all directions. So alpha along the x direction will be same as alpha along the y direction. But and such materials are called isotropic materials. Isotropic means same properties in all directions. But there are some materials which show different properties in different directions. Okay, you may have experienced this in real life also, like some stretchable materials. They are easy to stretch in one direction, difficult to stretch in a perpendicular direction. So for some materials, alpha along x direction may not be the same as alpha along the y direction. Such materials are called anisotropic materials. Okay, different properties in different directions. Okay. So we will discuss both cases. We'll derive it generally. Now, if length is L naught, breadth is B naught, the original area is L naught B naught. Then if length expands and breadth also expands, then the new area becomes new length into new breadth. So it becomes L naught B naught 1 plus alpha along the x-axis delta t multiplied with 1 plus alpha along the y-axis delta t. Okay. Now we want beta in terms of alpha. Okay. How do you get beta? Change in area divided by original area multiplied with the temperature difference. Now, how do you get change in area? You will have to subtract this final area minus the initial area. Okay. Final area is L naught B naught 1 plus alpha x delta t into 1 plus alpha y delta t. That is the final area. Minus initial area is L naught B naught. So what I'm going to do is I'm going to take L naught B naught common and I'll simply write minus 1 here. Divided by original area. Original area is L naught B naught. Temperature changes delta T. So this gets cancelled. Fine. What will you be left with? Multiply those two brackets. You get beta is equal to 1 plus alpha x delta T plus alpha y delta T plus alpha x alpha y delta T squared. Okay, that is when you multiply those two brackets and there's a minus 1 also. Whole thing is divided by temperature change delta T. So the ones will get cancelled now. Look at what you are left with. Alpha x delta T plus alpha y delta T plus the third term. Now alpha values we have just seen. For steel it is about 10 power minus 5 per Celsius degree. Usually for solids it will be in that range only. 10 power minus 4, 10 power minus 5 range. So this is approximately 10 power minus 4. This is also 10 power minus 4 approximately. This is 10 power minus 4 into 10 power minus 4. This will be 10 power minus 8 range. This third term is negligible compared to the first two terms. So if you ignore that, what will you be left with? Alpha x delta T plus alpha y delta T divided by temperature difference. Delta T is common in numerator denominator. It will get cancelled. You get it as alpha x plus alpha y. Very simple. Therefore, the coefficient of areal expansion is the sum of coefficients of linear expansions in two perpendicular directions. Now, if the solid is isotropic means having same properties in all directions, then you can write alpha plus alpha basically becomes 2 alpha. So coefficient of areal expansion is 2 times coefficient of linear expansion. Simple. Similarly, you can also prove that gamma for an isotropic material is 3 times of alpha. Okay. So alpha is to beta is to gamma, if you see, will be 1 is to 2 is to 3, provided it is isotropic. If it is anisotropic, then you will have to write alpha x plus alpha y if you want beta. And if you want gamma, it will be alpha x plus alpha y plus alpha z also. Third dimension also you will have to consider. That is how alpha, beta, gamma are related. So what does this show us? This shows us that if you know one of them, it's like knowing all three of them. Okay, provided it is isotropic. If they don't specify anything in the question, you will assume it is an isotropic material. Alpha, beta, gamma ratio will be taken as 1 is to 2 is to 3. Okay. Next, let us also discuss about thermal stress. See, when you raise the temperature of a material, usually materials tend to expand. But for them to expand, you need to provide space. Okay, we saw one image yesterday of railway tracks, okay, becoming curved. That is because they did not provide space for the tracks to expand. Fine. Now, tracks are made of steel. How can steel bend like that? Or how can any material bend when you apply force on it, when you apply stress on it? Okay, we had discussed this in the chapter solids. When you apply stress, you can deform a solid. So if the track is getting deformed, it means there is stress generated in it. That is when it gets deformed. And what generated that stress in the deformed track? Raise in temperature only, no? Okay. That is what we call as thermal stress. This is not a new kind of stress. It's one of the stresses that we have already discussed. Now, if you remember in the chapter solids, we had studied three different kinds of stress. Longitudinal. Longitudinal stress tends to increase or decrease the length of an object. We had discussed tangential stress, and we had also discussed volumetric stress. Okay, these are the basic kind of stresses that are there. If any of them arises due to temperature change, you call it thermal stress. Okay, so thermal stress is not a new kind of stress. Basically, when temperature rises, the material would want to expand. If you don't allow it to expand, it will develop a stress. Same with decrease in temperature also. If temperature is decreased, the material would like to contract. If you don't allow it to contract, stress will develop. Okay, fine. Consider two rigid boundaries. Let's say an object is placed between these boundaries. Let's say it exactly fits at a particular temperature, it exactly fits between these two. Some long cylindrical object, let us imagine. You can think of it as a rod also. Okay. So at temperature is equal to, let's say, T1. Let's say the length of the object is L1. That's the exact distance between these two rigid supports. Now you raise the temperature of this object. If you raise the temperature of the object, naturally it will try to expand. It will have a tendency to expand. But the rigid supports are fixed. Okay. So what is happening? The object wants to expand, means it wants to increase its length to a new value somewhat like this. See, actually expansion will happen everywhere. I should not show it on one side. Okay, it will be like this. It will try to expand everywhere, but just to get an idea of how much it has expanded, I'm showing you like this. This is the expansion delta L. This is the original length L1. Here also L1 is there. Some extra length is there. If it was free to expand, it would have expanded like this. Okay, but the object is not free to expand. So it will still have to, it will be forced to still occupy a length L1 itself. It wants to occupy a greater length, but we are forcing it, okay, to occupy a length L1. So there will be stress developed in it. Now tell me, okay, wait, this new length is at a higher temperature, right? So this is at higher temperature. Let's call it T2. Fine. We are not allowing it to take that new length. So tell me, are we compressing the rod or stretching the rod? What kind of stress is developed in it? Compressive stress or tensile stress? If you stretch something, tensile stress will be developed. If you compress something, compressive stress will be developed. What kind of stress is developed now in this rod? You have raised its temperature, but you didn't allow it to expand. Okay, Vanilla has given the answer compressive stress. That is correct. We are forcefully compressing it to a shorter length. Had the rod been free, it would have assumed this much length. Okay, we are forcefully making it shorter. So there is compressive stress. And since this is in terms of length, you can say longitudinal stress is developed. Compressive longitudinal stress is developed. Fine. The longitudinal stress, longitudinal strain, they are related by Young's modulus. Those of you who have studied the chapter solids, you would be aware of this. Young's modulus, by definition, is longitudinal stress divided by longitudinal strain. Therefore, the longitudinal stress developed in this object, okay, in this rod, would be Young's modulus Y multiplied with the longitudinal strain. Okay. How is longitudinal strain measured or calculated? Change in length divided by natural length. Okay. Now, this is slightly tricky. So, our aim is to measure the stress developed. The kind of stress we are talking about here is longitudinal stress. It is developed due to a temperature change, so you call it thermal stress, but the kind of stress we are looking at here is longitudinal stress. Young's modulus into how much is the strain. Now, see, we can calculate delta L. Delta L is equal to L1 alpha delta T. So delta L is known to us. But what is delta L here? Delta L is the length by which it would have expanded had the rod been free. So that free length is what you call as natural length. So at the new temperature T2, that length is the natural length. Naturally, the rod would be at that length. You are forcing it to take a shorter length. Okay. And how much shorter? Delta L. You are forcefully decreasing its length by delta L. Okay. So this same delta L, which we got from thermal expansion, can be used here. That is the change in length that you are forcing. So L1 alpha delta T is the forceful change in length divided by what is the natural length. Natural length is not L1. At the new temperature, natural length is L1 plus delta L. Okay. This is the tricky point. Usually students in a hurry, what they do is they take natural length as the original length L1. Okay. No. At the new temperature, when the rod is free, what length it would have taken? When there is no stress on the rod, what length it would have assumed? That is what you call as natural length. Okay. But if we simplify this, numerator is L1 alpha delta T. Let it be. Denominator, you have L1 plus delta L. Delta L is how much? L1 alpha delta T. Okay. Now L1 is common in numerator, denominator, it will get cancelled. You'll be left with Y alpha delta T divided by L1 got cancelled in the denominator. You'll be left with 1 plus alpha delta T. Okay. Now alpha values for solids, they are in the range 10 power minus 4, 10 power minus 5. Change in temperature also will be quite small compared to 10 power minus 4, 10 power minus 5. If you multiply with delta T also, this will be a small term. If it is very small, you can ignore it. And if you ignore that compared to 1, if that term is ignored, you will be left with Y alpha delta T. So if alpha delta T is very small compared to 1, then okay, the thermal stress is y alpha delta t itself. Okay. But if alpha delta t is not very small compared to 1, means it is significant. That depends on the problem. Okay. If alpha delta t is significant, then thermal stress expression would be y alpha delta t divided by 1 plus alpha delta t. Okay. Then you will have to consider that alpha delta t in the denominator as well. So whether it is significant or not depends on the data given in the question. And how do you decide whether it is significant or not? If it is less than 0.1, okay, I'll write it here. Alpha delta t less than 1/10. 1/10 means 0.1. Then you can ignore it. If it is greater than that, you cannot ignore it. Okay. Less than equal to also. Let us avoid that confusion. If alpha delta t is more than 0.1, don't ignore it. Okay. Usually in books, you'll find this formula. Y alpha delta t. Only till there you will find. But the actual formula is y alpha delta t divided by 1 plus alpha delta t. Okay. So here we talked about longitudinal stress created in a rod due to thermal expansion. Okay. Now similarly, see here we are restricting the expansion of length. So it results in longitudinal stress. If you restrict the expansion of volume altogether, it will result in volumetric stress. Then you will have to use bulk modulus. Okay. Let's solve one problem like that. And let me quickly remind you what is bulk modulus. This beta is for bulk modulus. So I'm using the subscript naught. So beta naught bulk modulus is basically volumetric stress divided by volumetric strain. Therefore, if you want volumetric stress, it becomes bulk modulus multiplied with volumetric strain. How do you calculate volumetric strain? Change in volume divided by natural volume when there is no stress. Okay. How much is the volume it would have occupied? That is natural volume. Okay. Beta naught is bulk modulus. Keep that point in mind. Now I want you all to derive an expression for volumetric stress caused by thermal expansion. So how do you go about doing that? Assume some object has initial volume V naught at temperature T1. Okay, this is the free volume of that object at temperature T1. Now when you raise temperature, volume will increase. You know how to write expression for increase in volume in terms of gamma, change in temperature and all. Okay, so let's say temperature is raised by delta T. You can find out new volume. If it is allowed to expand, it will take that new volume. But suppose we don't allow it to expand. Okay. So the object is not allowed to expand. It wants to expand, but you are not allowing it to expand. So what will happen? Stress will get developed. Derive an expression for volumetric stress. And I have to give you gamma value. So assume gamma is given to you and bulk modulus beta naught is also given to you. In terms of these, I want you to derive the expression for volumetric stress. And if you want to make any approximation, you can make. Okay, like here, for longitudinal thermal stress, one approximation is that alpha delta t is very small. If you take that approximation, the answer you get is y alpha delta t. So if you need to make such approximations, you can make. Okay, try this all of you. This usually you don't find in books. They talk about longitudinal stress. They call that itself as thermal stress. That's okay. But this is also possible. No? You can prevent volumetric expansion and you can be asked to find out volumetric stress. Yeah, do this quickly. Okay. See, suppose there is an object. You can take an object of any random shape. Let's say this is the volume initial volume V naught at temperature T1. If you raise the temperature, this object would expand. It will expand in all directions. On the screen, it looks like areal expansion, but you have to imagine it in 3D. Okay, in 3D, it will be volume expansion. Okay. So this is the new shape it would have liked to take. Natural shape at the new temperature is this. Okay, or natural volume at the new temperature is this. Expanded volume. Fine. So this is, let's say, V dash at the new temperature, which becomes V naught into 1 plus gamma delta T. But what are we doing? We are not allowing it to expand. We are forcing it to take that smaller volume. So we are compressing it by delta V. So basically it is compress. I mean, it wants to expand by delta V is equal to V naught gamma delta T. You are not allowing it to expand. So compression becomes V naught gamma delta T. Okay. So that's the change in volume that you are forcing. And what is the natural volume at the new temperature? V naught into 1 plus gamma delta T is the natural volume at the new temperature. That's all. You know change in volume and you know natural volume. Then you can tell how much is the stress developed. Volumetric stress simply becomes bulk modulus multiplied with change in volume divided by the natural volume. Therefore, volumetric stress now is bulk modulus beta naught multiplied with change in volume is V naught gamma delta T divided by natural volume at the new temperature is V naught into 1 plus gamma delta T. V naught gets cancelled. You get a formula very similar to that longitudinal stress developed. There it was Y alpha delta T, where Y is Young's modulus. Here it is bulk modulus gamma delta T divided by 1 plus gamma delta T. If gamma delta T is small, you ignore it. Otherwise, don't ignore. Okay, so if an object wants to expand and you don't allow it to expand, stress will be developed in it. That stress is called thermal stress. Okay, but it will be of one of these kinds, longitudinal, tangential, volumetric. Fine. So we'll stop it here for now. Tomorrow's class, we will discuss something called relative thermal expansion. Maybe solve a few problems based on thermal expansion. And after that, we will start discussing calorimetry. Okay, like how much heat needs to be supplied to bring about a certain change in temperature. And after that, conversion from solid to liquid, melting, freezing, okay, boiling, I mean, vaporization, condensation, those processes also we will discuss. Okay, thank you all. We'll continue tomorrow.